Hey math people! So I should have a video out on applications of derivatives. That has to do more so with like concavity and when things are increasing and decreasing and tangent line, blah blah blah. All those things are great, not as good as this stuff. Real applications of derivatives. So today we'll talk a little bit about particle motion and related rates. Okay, starting off with our first one. Find the displacement and distance traveled when given the position function, that is s of t. And we're giving it a start and end point from, say, 5 seconds to 6 seconds. There is a difference between displacement and distance traveled. Here is a pictorial example of that. Let's just say you have a point A, and you want to go to a point B. The path you take is a running path. So maybe you are running through your neighborhood, and you want to take the long way there. You're going out for ice cream and you want to really earn it, so you take a longer path there. In which case your distance traveled is a heck of a lot more than someone else in your household who just went straight there. They were not having it. They said, no, it's not worth a run. I'm just going to go straight to the ice cream shop to get myself some ice cream. So with that said, both of you had the same displacement. You didn't have the same distance traveled though. Twisty, turny guy, you traveled quite a bit more than straightforward path guy. Distance traveled, always positive, and displacement can be negative. If you go backward 1 unit, 1 foot, you would have a displacement of -1, but your distance traveled is the absolute value of that. So there are two things to be wary of. One being, well, what if you go backwards, in which case you take the absolute value for distance. And two being, well, what if you do some twists and turns, in which case you have to do a little bit of work to differentiate the difference between displacement and distance traveled, which will happen here. So we have a position function that happens to be a parabola. So let's worry about displacement first. All that really cares about is where you are at 5 seconds and where you are at 6 seconds. That's it. So the math here is quite simple. I want to find the difference between these 2 points, and this is for displacement. Where was I at 5 seconds? Where am I now at 6 seconds? For that, calculator is nice and handy. I could do this by hand, but it's not worth your time or mine. So we are 56 units backwards, 6 seconds in. So if you were to plug in 6, -56 shoots out. And actually, ironically, or maybe this was intentional for the sake of learning, we're also 56 units backwards at 5 seconds in too. So the total displacement here is 0. I didn't go anywhere. So from 5 to 6 seconds, I kind of might have went forward a bit and then backwards in just the 1 second period, or I went backward a bit and then forward in that 1 second period. And it's kind of like I didn't move. So total displacement here, 0. Distance traveled though, that's another thing. We know that this parabola never flatlines. We know that it has a curved nature to it. So we did travel some distance, we just ended up back to where we were. We have to figure out how to find that. The best thing to look for, or rather the best way to use a more calculus lens, is to figure out when this thing switches directions. And we can determine that by taking the derivative. So let's do that. If I know s of t, t squared minus 11t minus 26, velocity is actually the same thing as s prime of t. I can figure out when I have a positive velocity and when I have a negative velocity. So taking that first derivative, it's 2t minus 11, and well, that goes away because we're taking the derivative of a line, and well, this goes away because we're taking the derivative of a constant. So that's actually it. It's just 2t minus 11. The way we determine when we switch the direction we're going in, either forward or backward, we want to figure out when our velocity is 0, when we go from a moving forward, which would be a positive, to a moving backward, which would be a negative. So let's set this thing to 0. Now, this should start to make sense. We're looking from 5 to 6. If we had a displacement of 0 from 5 to 6, and this is a parabola, then very clearly here we're looking at this local region near the vertex of the parabola. ultimately what I'm finding here is the vertex of the parabola. If I add 11 to both sides, I get 11 is equal to 2t. And that's a one-step process now. T is equal to 11 over 2, which is 5.5. So what is this saying? At 5.5, I actually have a flat line derivative. This parabola, right at an x value, and this is all negative actually, so this will be below the x-axis. Maybe I'll put the x-axis above it. Let's do it this way. This is at 5 seconds, and this is at 6 seconds. You'll note here that they have the same exact displacement. But we go backward a bit, and then we go back forward. So at 5.5 seconds, we are a perfectly flat line. If we were to find a tangent line at 5.5, it would be perfectly horizontal. So what does this tell us? We have to actually split this into pieces. We need to find the total displacement from 5 seconds to 5.5 seconds. Take the absolute value of that, and then add it to the displacement from 5.5 seconds to 6 seconds. That way we kind of bypass this idea of encountering a total displacement of 0, because we're looking at the total amount of time we're going backward plus the total amount of time we're going forward, or total amount of distance rather. We're going to add up those two distances together. That will get us total distance traveled. So nothing too bad. We can rely on our calculator once more, although math is not necessarily something you need to use a calculator for. Sometimes it's nice just to do some really simple arithmetic with it. The whole beauty behind the calculus is, well, when we don't have to rely on the calculator for these things. So this was for displacement. So for distance, what we want to do is something very similar. We want to take the absolute value from s of 6 minus s of 5.5, and then add that to the absolute value from 5.5 to 5. Okay, we already have some of those values from above, so I'm going to plug in those negative 56s accordingly. So here's a negative 56 here. I don't know s of 5.5 yet. I have to throw that in my calculator to figure out what that is. But I do know s of 5, and it's negative 56 again. Okay, so what is s of 5.5? It's negative 56.25. Okay, so both these things are the same expression. Really, we just have to find one and then double it. So over here, it looks like we're getting 0.25. So you take a quarter plus a quarter. This is a quarter, right? Yeah, this is going to be a quarter. Looks like total distance traveled is a half. So whatever the units are here, we'll just say that they were we'll just say the units are in feet. So here we would say 0 feet and a half a foot. So big takeaway here, difference between displacement and distance traveled. You have to consider the direction and ebb and flow, the forwards and backwards, or the lefts and rights with distance, whereas displacement, nah, you don't have to worry about that at all. Just worry about where you start and where you finish. Okay, so the next problem is involved. There's a lot you can ask with particle motion, and we're asking, well, a good amount of what we could ask. So we're given this position function here, s of t, and it's cubic. We'll also say that any positive output will just mean units to the right, and any negative output will be units to the left. So we're going to go left-right, not up-down, not forward-backward. This time around, we're going to go left-right. There's a few different ways you can ask that. So one thing we should know and love with any particle motion style problem is that s of t, this is our position function. Great. S prime, though, well, this is secretly our velocity function. And s double prime, well, that's secretly our first derivative of velocity, which happens to be our acceleration function. So this is a key relation between them. You take derivative of position, you get velocity. You take derivative of velocity, you get acceleration. And the pattern continues. You can take the derivative of acceleration to get the jerk function is what it's called. And some of my students did research on the fact that you can keep going, and somehow, some way, you get some sort of snap function, crackle function, and pop function. I'm not sure. I don't know much about that. I do know that these three are really common. Not sure about the serial, though. Anyway, you can keep taking derivatives, but at that point it's not worth it. Talking about the rate of change is great, but talking about the rate of the change, not really for me. Let's talk about this guy now. Times when the particle switches directions. The way we want to find that is when we encounter a velocity of 0. So let's take the first derivative here. We get velocity, set it to 0, and those will be the moments where we switch directions, so long as when we run a first derivative test, it switches signs. That's a small stipulation that's attached with it. So we're going to do that. Taking that first derivative, we end up getting v of t is equal to 3t squared minus 44t plus 121. Oh man, we could have chose nicer values. Because unfortunately when I set this to 0, is there any way out of the quadratic formula here? Maybe, if this is factorable. I'm going to do the quadratic formula though. So I'm setting this to 0. Using my quadratic formula here, I'm going to get negative b, so it's going to be 44 plus or minus the square root of 44 squared, so b squared minus 4ac. And this is going to be all over 2 times 3. Okay, so it turns out this is factorable for sure. I was actually getting a nice pretty expression for the radical. So this was factorable, but we can still use quadratic formula. You end up getting the two solutions of 66 over 6, which is 11. And you also get, whatever this is going to be, 22 over 6, which is 11 over 3. So what we should do is we should run a first derivative test. We should draw a number line here, which will be our velocity. And we know that at 11 over 3 and 11, we switch signs. So all we need to do with this first derivative test is simply verify that we have sign changes on the left and on the right of these potential candidates. So it's tempting to ask, why do you have to do that? Well, here's the thing. We're talking about switching directions. What I could do, just in life, I could walk forward, stop for a bit, and then continue to walk forward. I didn't switch directions there, but I did have a moment where my velocity happened to have been exactly 0. So if you didn't test, if you didn't run a first derivative test, and you just assumed at this moment was the moment I switched directions, you'd be wrong, because I continued to move forward. I simply just stopped. So that's what we're hunting down when we run a first derivative test completely and check the signs. So with that said, if I plug in small, if I plug in, say, 1, what shoots out? It's a positive number. If I plug in middle, which is between, what is this? This is about 3 or 4, right? So let's plug in 10. That requires some thinking. Should be negative, okay? And if I plugged in 1,000,000, this thing's going to take control and this will be positive. So yeah, in this situation, nothing too tricky. We did switch signs. So we actually implicitly answered some of the questions here. How about answers will be in red? I like that. So answer to first part, when I switch directions, indeed, I switched directions at 11 over 3 and 11 seconds. So when t is equal to 11 over 3 and 11 seconds. Second one, let's do interval where we're moving left next. We stated earlier that any negative output would be units to the left and any positive output would be units to the right. So in which case we have a negative velocity from 11 over 3 to 11. So that would be moving left in that situation. So from 11 over 3 to 11 we are moving left, which would then mean the rest would be moving right. something minor that almost all of these problems come with is this idea that time is always greater than or equal to 0. Doesn't really make too much sense to track negative time. In fact, it doesn't make any sense at all unless we can time travel. So with that said, it's very common to attach, well, t must be greater than or equal to 0 to these problems. So with this said, we are going to start at 0 seconds. So from 0 to 11 over 3. Then we're going to union this with 11 to infinity. So there's no upper bound to this. There's no cap. I guess we just keep going faster and faster and faster forever. The next problem asks for acceleration. So acceleration we shall do. And maybe I'll do that with that empty space over here. Let's take the next derivative. So a of t, what's that going to be? So our constant's going to go away. We now have 6t and then minus 44. So we want to find an acceleration of 0. That's pretty straightforward. We set this thing to 0. So 0 is equal to 6t minus 44. We get 44 is equal to 6t. We get t is equal to 44 over 6. What is that? Did we do that earlier? No, we didn't do that earlier. So this is going to be 22 over 3. Okay, so about 7 point something. 7.3. Alright, but we're going to stick to the improper fraction because that's the mood I'm feeling. So with number 4, our acceleration is 0 at exactly t is equal to 22 over 3 seconds. Okay. We got 2 more when we're slowing down and speeding up. Those on the camera? Yeah, they are. Alright, the way we find slowing down, well, you can slow down in 2 directions. You could be going forward, and you could be slowing down going forward. You can also be going backward and slowing down going backward. So in this case, left and right. The way we want to consider speeding up is also the same thing. You can speed up going in the forward direction. You can also speed up going in the backward direction. So the way we kind of determine this, speeding up is pretty intuitive actually. Speeding up, if you happen to be going, so we'll say velocity and then acceleration. If you happen to be going with a positive velocity and you want to speed up, well, you want to make that velocity even more positive. So you want to accelerate. And likewise, if you are going in a negative velocity and you want to continue to go in the negative direction but faster, well then your acceleration would then also need to be negative. So for speeding up, you want matching signs for both acceleration and velocity. Slowing down is the exact opposite. If your velocity is negative, you want your acceleration to be positive. And if your velocity is positive, you want your acceleration to be negative. So how are we going to do this? This seems a little hard to track. Not too bad if you run a second derivative test next to your first derivative test. We can now say, well, okay, an acceleration, that's going to be the following line. 22 over 3, relative to these numbers, it's going to be about right here. 22 over 3. We just have to figure out what is going on to the left and right. If I were to plug in a small number to that, say like the number 0, a negative shoots out. And if I were to plug in a big number, a positive will shoot out. We need to figure out when these signs match. There's a, or rather, we got to figure out kind of the behavior of these signs from 0 to infinity. And a component of that is figuring out when they match, and that's for speeding up. So for slowing down, we want to figure out when they don't match. When you have a mismatch of signs when comparing our acceleration to velocity at any given point. So right at 0, right off the bat, we are actually negative in our acceleration, and we are positive in our velocity. So actually I'm going to start writing down the solution to slowing down. Man, I've used quite a bit of number of colors for this one. Here we are. Okay, so from 0 seconds, and we start on 0, we are going up with our velocity and down with our acceleration. And this is true all the way up until our very first number where we either switch our velocity or switch our acceleration. So it's true all the way up to this moment right here, which happens to be 11/3. In which case we switch our velocity at that moment. Okay, and then at 11/3 I get a negative velocity, so actually my velocity matches with my acceleration for a bit now, because this is where I'm at on my number line, and at 22/3 that does switch. So I'm going to say union here, so I'm no longer slowing down, I'm actually speeding up from 11/3 to 22/3. So I'm going to start my answer for speeding up, 11/3 to 22/3. So right now I am speeding up in the negative direction, and all of a sudden, bam, I hit 22/3, in which case my acceleration now goes positive. So in this little small interval, I have a negative velocity, but a positive acceleration. So in which case, those don't match. I'm actually back to slowing down again from 22/3 up until the next moment, one of the two switch directions. So from 22/3 to 11, I'm actually slowing down. And then what happens at 11? At 11, I then turn to a positive velocity, and I already had a positive acceleration at that moment, so it's positive, positive, in which case I'm then speeding up forever and ever and ever, forever accelerating and forever moving in a positive direction, positive velocity. So with that said, I'm going to union this from 11 to infinity. And, it might be a little easier to see it chunked this way if I were to draw. Ruining my red marker just a little bit here. But, yeah, we can continue to write in red. So this will be positive, negative. This will be negative, negative. This will be negative, positive. And this will be positive, positive. So actually, this problem's kind of nice in the sense that I have every combination. So here I'm slowing down. Here I'm speeding up in the negative direction. Here I'm slowing down again. And here I'm speeding up in the positive direction. So all 4 intervals are accounted for. And this is an infinity in our slowing down intervals and speeding up intervals. Okay, that one was a little involved. Let's do some related rates now. So related rates just means that if you have a function that relates some ideas together, you can also make connections on their rates over time via that same function. That's fancy talk for what I'm going to do right now. It's actually not that crazy. Step 1, figure out what that said function is in play. Let's do it through a problem. People begin to gather around black pen, red pen in the streets. Once they realize he does a lot of cool calculus. The radius of the crowd increases at a rate of 4 feet per second. How fast is the area taken up by the crowd increasing when the radius is 7 feet? Okay, so they keep mentioning radius a lot, and they also asked for an area. Radius, area, we should be playing around with area of a circle, which is pi r squared. So what I want to do is I want to rewrite this thing relating their rates together over time. I want to find the derivative with respect to time. And we're also keeping in mind that the area and radius, they're functions of time. So we have to do a bit of chain rule with that said. So what I want to do is this. I want to take the derivative of this expression, knowing that a and r are both functions of time, so they are not constants. This is not a trick question where 0 is equal to 0. No, these are functions, and within them is the variable time. So with that said, I want to find the derivatives of them with respect to time, ddt. So the way this is going to work, derivative of function a is going to just be dA dt. Just taking the function with respect, or derivative with respect to time. Pi is a constant. I don't have to do much with him. He's just going to sit there and do his own thing. When taking the derivative of something squared, you actually have to just generally do a power rule here. So this is going to be 2r. Don't get me wrong. That's how you do derivatives if you have something raised to a power. However, r is a function of t. So we have a function on the inside. If you're taking the derivative of a function in a function, you need the chain rule. So the derivative of r is just dr dt relative to the fact that r is a function with respect to time. So we're going to sneak in a dr dt there. And this is actually the function we're going to be playing around with. At this point, we plug and chug. We plug in all of our values to solve what we're looking for. Here I have 1, 2, 3 unknowns in play, and hey, look at this. I have 1, 2 numbers being asked for the third. So the math at this point is nothing crazy. We have a radius that is increasing at a rate of 4 feet per second. Well, is that going to be dA dt? Is that going to be r? Or is that going to be dr dt? It's a rate, so it's not r. My two rates are here. Well, very clearly here, it's a radius of a crowd. So in which case, it's going to be dr dt. So I'm going to plug in a 4 for that value. And then how fast is the area taken up by the crowd increasing when the radius is 7 feet? Okay, so we also know that the radius here is 7, and r represents our radius here, so we're going to plug in 7 for that. In which case, I now have all of my knowns plugged in. I can solve for my unknown, which is how fast the area is increasing. So that's dA dt. It's my rate that the area changes over time. In which case, do some simple multiplication. Do I happen to know what 14 times 4 is? That's 28 times 2, which is 56. So this is going to be 56 pi, and we should attach our unit, right? So it's a rate. It's not going to be just feet, and it's not going to be even feet per second. It's a changing area. It's a rate of an area. So I know my time is seconds. I know my feet is the unit at play. Area is squared, so it's going to be feet squared per second. So a few little tricks here. One being the chain rule. 2 being figuring out what goes where when you plug in. And then 3 being, well, figuring out the unit at the very end. Next one on the agenda is a classic. It's a sliding ladder. And maybe to you that's not a classic, but to a calculus teacher this is certainly a classic. Almost every calculus teacher should talk about the sliding ladder as a related rate problem. It's probable that you did if you're watching this video. Anyway, 17-foot tall ladder. Is ladder spelled that way? Ladder is spelled that way. A 17, you ever read a word and it's like, man, I read that a lot of times in a row or wrote it a lot of times in a row. How do you spell that? Anyways, moving on, a 17-foot ladder is leaning against a wall and is sliding down the wall. The base of the ladder is sliding away from the wall at a rate of 7 feet per second. Okay, how fast is the top of the ladder sliding down when the top of the ladder is 8 feet from the ground? You got a ladder leaning against a wall and it is simply sliding down. Perhaps it wasn't fortified at the base and it's a marble floor. So what we want to do is we want to find the rate, the rate of the top of the ladder as it slides down the wall. Hey, how about this? How about we draw it? That's a great way to start these related rate problems. Draw it and see how that might help. This is my 17-foot tall ladder. This is the only length that doesn't change over time. However, we are playing around with the specific instance when we are 8 feet. Is this the 8? When the top of the ladder is 8 feet from the ground. Yeah, so this is the 8 feet. You're looking at this specific instance when the top of the ladder is 8 feet from the ground. And actually, in a situation like this, you should be, or your Pythag triple alarm should be ringing. This is a famed Pythag triple. It's an 8, 15, 17 Pythagorean triple. And that's a great setup of the problem. So this ladder is sliding down. This is going downward, and this is going outward. Okay, so what have we used thus far? We have used this 8. We have used this 17. But how the heck do we use this 7 feet per second? We got to set up an equation. We got to set up a function to play with and take the derivative of it with respect to time. So we just use the Pythagorean theorem. How about we write it as an expression now? Here's the thing though, as the ladder slides down, we have this ever-changing y value, we'll call it. We have this ever-changing x value, and then we have the constant length that is the ladder. So with that said, I'm going to write Pythag with 2 unknowns and 1 constant. X squared plus y squared is going to always be equal to 17 squared. I don't know what 17 squared is, but 256? I'm not sure. I don't even know why, I guess. Doesn't matter because of what we're about to do shortly. What we want to do is we want to take the derivative of this thing with respect to time. 289. One of those two. Okay, so let's do that. The derivative of x squared is 2x. That's not too bad. Except chain rule. X is a function of time. So derivative of x thereafter is dx dt. Plus, well, this is just going to be 2y. That's good and fun. But again, y is a function with respect to t, so we need a dy dt thereafter. Derivative of 17 squared, this is when it didn't matter that I didn't know 17 squared. It's 0 because it's a constant. It doesn't change over time. The length of the ladder doesn't magically shrink as time goes on, or increase as time goes on. It stays the same, it's a constant. This is a rate function now. So we have 1, 2, 3, 4 unknowns. We have 3 numbers. Well, do we have 3 numbers? 1, 2, 3. Yeah, okay. We have 3 numbers. We're done with that 17 though. We're going to be using this 15 instead. Let's plug them in and find our unknown. Let's see if we have our x value. Our x value is going to be the base. So this is x and this is y. So it's going to be 15 for this x. Okay. Dx dt. Do I happen to know that, or is that what I'm looking for? When the top of the ladder... Okay, so how fast is the top of the ladder sliding down? When the top of the ladder is 8 feet from the ground, okay. The base of the ladder is sliding away at a rate of 7 feet per second. This is my rate for the base, dx dt. That's where I plug in my 7. So for this expression right here, dx dt, in goes a 7. All right, what about y? That will be this length right here, and that's specifically at the moment where we're 8 feet from the ground. So here we're going to plug in 8. And well, dy dt is what we were looking for all along. We're looking for how fast the top of the ladder is sliding down. So with that said, we're going to keep dy dt as, well, dy dt. Okay, so now all that's left is some algebra. This is going to be 210. This is going to be 16 dy dt. Now we're looking at a 2-step equation. Move the 210 and solve for dy dt, and then you're done. So dy dt should equal 210, or sorry, negative 210 over 16, which can be simplified. Divide by 2, divide by 2. So that would be 105 over 8. Okay. Makes sense that it's negative because I'm sliding down. My rate is downward. Heads up on that. Just thinking about what my units are, it's the same as the rate of our dx dt. It's going to be feet per second. for our dy dt. So negative 105 over 8, whatever that comes out to, is our final answer. Classic ladder problem. All right, last and final one on the list is a classic again. I know that the sliding ladder is a classic, but the cone, the leaky cone, is as well. Oh no, a cone is leaking. It's 10 centimeters tall with a radius of 20 centimeters. The water level is decreasing at a rate of 2 centimeters per second. At what rate is the volume of the water in the cup changing when the water level is at 5 centimeters? Let's start circling the important information. There's some numbers here. The two static numbers, so just simply the length of the radius and the height of the cone, 10 centimeters and 20 centimeters. Just like the last problem, it's best to draw the situation if you don't know how to start it immediately. So I'm going to try to draw a cone with these characteristics. It's got a pretty wide radius, it's not too tall. So this right here is fixed at 20 centimeters. And the overall height of the cone is fixed at 10 centimeters. Okay. Water level is decreasing at a rate of 2 centimeters per second. That's great, but we're going to use that later. Ideally, the situation is just set up this way. I have some sort of water level, and it also has a radius, and it also has a height that changes. So now we have two rates at play instead of one, which is why it's a classic. It's the easiest setup case for two rates outside of just the initial one changing like the volume. So three rates at once actually. This is our situation. So let's come up with an equation now. It should be pretty obvious what the equation is at play. It's just straight up going to be the volume of a cone. And I want you guys to try to think about what the potential problem is if I attempted right off the bat to find the derivative with respect to t of this expression. There's an issue, or it's not an issue, it's fine, but it just means more work. So try to think of what that is right now. Time's up. Yeah, you got it. I heard you at home. You said, well, there's a radius and a height, and they're both functions of t, so therefore, if I'm taking the product of two functions, we're going to need the product rule. You'd be totally correct, we would. There's a way around that, and that's the way I'm going to show you. Let's not do it the product rule way, it's just more complicated. Let's do it the easy way. What I can do is I can begin to see that my dashed black triangle is somehow related to this smaller blue triangle, which would be the triangle created by the water level. It's a proportion, a throwback to maybe 8th grade. I'm not sure when you last talked about proportions, learned proportions. You probably did it in geometry at least. Anyway, I have this unknown radius that changes over time, and I have this unknown height that changes over time. But I do know that this is always 20 and this is always 10, so I can establish a proportion. The ratio of my radius to height, r over h, is always going to be the same as 20, which is the radius of large, the largest when the cone is filled completely, and the height of the water level when the cone is filled completely. This is always true. This is a proportion. So actually I can establish a relationship between r and h here. This is just 2. So what does this imply? It implies that r is just equal to 2 times h. I can actually just sub that in right now to avoid this nonsense that is a function times a function which calls for product rule. I don't want to play that game. So I'm going to plug in this 2h right now. I'm going to say that the volume here in this specific cone is also equal to 1/3 pi, but instead of the radius squared, since I know radius is the same as 2 times the height, I can say 2h squared times h. Some math next. This is going to be 1/3 pi. Oh, I did the h in the wrong, or the square in the wrong position. Sorry. I'm squaring all of the radius. If the radius is 2h, I'm squaring all of 2h. So 2h squared will be 4h squared times h. And then after some cleanup here, I have 4/3 pi times h cubed. Okay, I now have my volume expressed as just one variable, which makes life so much easier. Finding my dv dt here, nothing too bad. I can then say, well, all right, d dt of this mess, okay, that's going to be dv dt. These are just constants, so I'm going to rewrite them. 4/3 pi times, well, okay, h cubed. Let's do some power rule at first. It's going to be 3 times h squared. However, h is a function of t, so we need that chain rule, and we're going to tack on that dh dt right here. And then bringing us to some canceled 3's, dv dt, which I will now sneak over here. It's going to be, what is that, 4, so it's equal to 4 pi times h squared. That's it. No, can't forget the dh dt. It's like, that doesn't seem right. dh dt. Okay, so how many unknowns? We have dv dt, we have h, and we have dh dt. Let's plug in the rest and call it a day. It's saying at what rate is the volume of the water changing, so dv dt is left as an unknown. H, we're looking for when the height is specifically 5. We didn't touch this value at all, now we touch it, because we're looking at that moment where we have a radius, or sorry, a water level of specifically 5. So that would be our H in this situation. Water level is how high up the water goes from the base. So this is going to be our 5. And then do I have a dH dt? Is there a dH dt in the crowd? Oh yeah, we didn't use this one either. So the water level is decreasing at a rate of 2 centimeters per second. So I'm going to plug in that 2 there. Okay, here's the big finish. So 4 pi times 5 squared times 2. I did a thing that I should be hypercritical of. One of these values is wrong. Water level is decreasing at a rate of 2 centimeters. So that's one of the tricky parts to related rates, is that you have to be very particular with your signs. This should not be just a 2. It's decreasing. The rate is going down. The way we express rates that go down, we do that with a negative number, so that should be a negative 2. The volume, at the end of the day, if we consider the contextual matter here, it's leaking, right? I'm going to draw, I don't know, some water droplets. It's leaking. The volume's going down over time. If you got a positive number, you should immediately be suspicious of your answer, because if the volume's going down and you're saying the rate is positive, something doesn't match here. We're going to get a negative this way. So 5 squared is 25, times 4, I can do that one, that's 100. So this will be negative 200 pi. What are the units for a volume that is changing, a rate of change for a volume? It's going to be centimeters cubed per second. We have centimeters in play. Clearly here the time was given as seconds. Volume is a cubed thing, which is our final answer. So the cone is a classic because we have these 2 separate variables. There are 3 related rates at play. We have the rate that is the height that changes over time, dH dt. We have the dr dt that changes over time, and we also have the volume as a whole, dv dt. Yeah, that's it. Okay, please continue to math on. I will do the same, and I'll see you in the next video.